This will be for the Khan Academy exercise, squeeze theorem. All right, so I'll give it to you in their words and then some of my own words. The squeeze theorem tells us that if we have three functions, f, g, and h, such that g of x is less than or equal to f of x is less than or equal to h of x for all x values other than x equals c in an interval around x equals c, and the limit as x approaches c of g of x equals the limit as x approaches c of h of x equals L. Then we conclude that the limit as x approaches c of f of x equals L. So the bottom line is this function here is the original function, okay? One function is going to be above it. Of course, the one that's greater than. And the other function is going to be below the original. All right, one is above and one is below. And it has to be, if we're doing the limit as x approaches c, this has to be true around the point x equals c. Okay? And if both the limit of the function above and the limit of the function below approaches a certain value L, then the original function also approaches that value L. So that's the point. For such functions, we say the graph is squeezed between the graphs of g and h, so it has no other option other than having the same limit as them, x equals c. All right, it should be more clear when we do the actual problems. So I just wanted to add, around the point that the limit is approaching, one function must be above and one function must be below the original. This is not necessarily true for all values of x. It's only around the point that the limit is approaching. All right, so we want to find a limit as x approaches 0 of x over sine of x. Direct substitution and other methods don't seem to work. So they gave us the graph of x over sine of x. They say estimate the limit is equal to 1. Okay, this is the graph of x over sine of x. We're doing the limit as x approaches 0. And you can see as the graph approaches from the right and as the graph approaches from the left, it clearly appears that the limit is approaching y equals 1 at x equals 0. Let's apply the squeeze theorem, or let's see what they did. All right, so Anish suggested that we use g of x equals x to the 3 plus 1 and h of x equals negative x to the 3 plus 1 in order to apply the squeeze theorem. All right, so does his suggestion seem to be correct? Well, let's see. The one in blue here, the function in blue is the original function. Okay, the one in blue is the original. And we're looking for the value of y as x approaches 0. So it has to approach 0 from both sides. Now, we said one function must be above, and we said that the other function must be below around the point that the limit is approaching. So since it's approaching right here, one function has to be above and the other function has to be below. Well, the one in blue is the original. Okay, maybe I can highlight that here. This one right here is the original function. Okay, in order to apply the theorem, one has to be above and one has to be below. Look at this function right here in orange. Right here, we're comparing it to the original one in blue. Right here, it's above the function, but then going right here, it's below the function. So that's no good. Same with the other side. If you look at the one here in maroon or red, the blue is the original. Right here, it's above the function. And right here, it's below the blue function. So that's no good. It has to be one function has to be above and one function has to be below. Here, it's crisscrossed. So that's no good. All right, answer B. And he suggests incorrect because it's not true that the output of one function is always below f of x and the output of the other function is always above for x values near 0. Why near 0? because we were doing the limit as x approaches 0. Okay, like I said, it has to be one above and one below for the values that are near where the limit is approaching. Answer B. All right, you can read the write-ups, but they don't really matter that much. Okay, we have the same function here for the original, x over sine of x, right here in blue. And they chose two new functions here, absolute value of x or negative absolute value of x. Let's look at them. All right, so it looks pretty good here. There's one problem, however. All right, we have the original function in blue. As x approaches 0, it looks like the limit is 1. Okay, and we do have one function above and one function below. Okay, even though this one crisscrosses here, but that's all right. Around the values of x equals 0.
3 o'clock.
Around the values of x equals 0 is all that matters, okay? All the way over here doesn't really matter. The problem is this function in maroon, as x approaches 0, this is between 2 and 1, so it actually approaches 1.5. And this one here, yes, it's below, but again, as x approaches 0, this right here is between 1 and 0. It actually approaches 0.5, okay? So since this limit here is 1.5 and this limit here is 0.5, that is no good, okay? They have to have the same limit for all three. So this limit appears to be 1, but the other two, the limits are not necessarily at 1, all right? It must be the same limit. So this one is no good. Answer C, Madison's suggestion is incorrect because it's not true that the limits of g and h are both equal to 1. Okay, I showed you one of them was 1.5 and one of them was 0.5, so that's no good. Has to be the same limit. All right, once again, the original function is the same, graphed in blue. They gave us two new functions here to use the squeeze theorem. Let's see. All right, the original is in blue. It's approaching this point right here. We have one function that's above. And this one in orange here, we have one function that's below. Okay, so that part works. All three of them are approaching y equals 1 as they approach x equals 0. Okay, so that's good. The original is in blue, one is above, one is below, so we are good on that. The answer is yes. His suggestion seems to be correct. Okay, the answer choices are the same for all of these problems. All right, really, you don't even need the write-up. All right, here's the original function in blue once again. The red or the maroon and the orange are the ones they use for the squeeze theorem. And you can see right here, the one in maroon, it is above for part of the function, but then it goes below for the other part. See, right here it's above, right here it's below. Same thing with the one in orange. The orange is below right here, but then it's above right there. Okay, like I said, one function has to be almost always above and the other one almost always below, at least around the points where you're approaching x equals 0 or whatever limit you're using. So this one's no good. Answer B, it's not true that the output of one function is always below and the output of the other function is always above. All right, here we have the original in blue. The maroon part here, it's above for part of it, but then it is below for the other part. Same with the one in orange right here. The orange is above, but then over here, the orange is below. All right, that's no good. All right, answer B. It is not true that the output of one function is always below and the output of the other function is always above. All right, if you get one wrong, just click on show their explanation and read their explanation, because this one is not that difficult, even if you have to repeat it.